Hello everyone, I am Dr. Sirajul Fazi. I welcome you in my YouTube channel. Today in this video, I am going to talk about equilibrium. So, what is equilibrium? You can see in this picture some of the more energetic particle escape. So, the second situations you can see, and finally liquid vapor equilibrium. So you can see here liquid and slowly some particles going in vapor phase and then equilibrium established. So friends, this is liquid vapor equilibrium. Liquid converted into vapor and vapor converted into liquid. So I will discuss some basic concept and definitions. What is the meaning of equilibrium? A system is at equilibrium if its free energy is at a minimum. Characteristics of the system do not change with time. The system is stable. Not change with time, the system is stable. If you change the temperature, pressure or composition, the free energy will change. You know the free energy. Now friends, pure substance required to express composition of phase in the system. What is the meaning of phase? Solid, liquid, gas. What is the meaning of components? Elements or compounds. So homogeneous portion of a system, uniform chemical and physical properties. Several phases may be present simultaneously. In principle, phases are recognizable and separable. System variables means compositions in terms of components, temperature and pressure. Now, phase rule. What is the phase rule? Coexistence of phases can only occur over a limited range. Phase rule is a rational relationship for determining the least number of intensive variables, and that can be changed without, so you can see here without the changing of the systems. So you can see here the relationship, and you should focus on this relationship and try to understand it, what is the meaning of this relationship. So you know here F is equal to C minus P plus 2. So what is the meaning of F, what is meaning of C, and what is meaning of P? So here P is the number of phases present, F is the number of degree of freedom, and C is the represents the number of components in the system. So friend, the number of degrees of freedom is the least number of intensive variables that must be fixed known to describe the system completely. So friends, system containing one component, you can see this is the phase diagram for typical. So I discussed this one, the number of degree of freedom. You know the number of degree of freedom is the least number of intensive variable that must be fixed known to describe the system completely. Friends, Examples of intensive variables are temperature, pressure and concentration. Now I will discuss about system containing one component. This is the phase diagram for a typical pure substance, pressure versus temperature. You can see the solid, you can see the vapor, you can see the liquid, and there is a three area, this and this. So at higher pressure the melting temperature would be higher, because the line between the solid and liquid areas, you can see solid and liquid areas, slopes slightly forwards, you can see little bit forward. So you can see the area and solid liquid vapor area, and then one point, and that point is triple point. So increase temperature at higher pressure, you can see original pressure is here, so this is a change. Now friend, increasing pressure at constant temperature changes liquid to solid and vice versa. So solid melts when the pressure drops to this value, and decrease pressure at a constant temperature. Now the same explanation for liquid vapor boundary. You see the increased temperature at constant pressure and decreased pressure at constant temperature. Now the point level at C, you can see the phase diagram is critical temperature. Note the process of sublimation as shown on the graphs below the point T. You can see the below the point T. Point T is called triple point. Where all the three lines meet, you must have a unique combination of temperature and pressure where all three phases are in equilibrium. Now normal melting and boiling point. You can see the pressure versus temperature at 1 atmosphere pressure, and now you see the vapor. So the friends, the phase diagram of water, pressure versus temperature, you can see the area of solid, you can see the area of liquid, you can see the area of vapor, and then you can see the T. In the case of water, the melting point gets lower at higher pressure. Why? So pressure, you can see 218 and 1 atmospheric pressure, and below 1 atmospheric pressure. Now temperature, you can see. So now you just keep in your mind the area of solid, liquid and vapor. Imagine loading the pressure on liquid water along the line in the diagram below. You can see pressure versus temperature, decreasing pressure at the constant temperature. So system containing more than one components. This is indicating one or more component, means vapor, vapor plus liquid, liquid, liquid plus vapor, vapor only. So condensed system. A maximum of 3 degrees of freedom is possible in two component system. More component, more degree of freedom. So F is equal to C minus P plus 2. In two component one phase system, maximum number of variable F is equal to 2 minus 1 plus 2 is equal to 3. Temperature, pressure and concentrations. We frequently choose to disregard the vapor phase and work under normal condition of 180 amperes. This is the universal truth. Now we can use planar figures instead of 3 dimensions. This will be easier. Condensed system when we only consider solid and liquid phase. So two component system containing liquid phase. The maximum temperature at which the two phase regions exist is termed the critical solution or upper consolute temperature. You can see the cyclohexane and aniline critical point, single phase and two phase, and you see this is temperature versus compositions. Now upper and lower consolate temperature. Temperature versus triethylamine in water percentage by weight, one phase, and then you can see they started out two phase, and you can see nicotine in water percentage by weight, two phase, one phase. Temperature versus nicotine in water. So two component system containing solid and liquid phase, eutectic mixture. Two components are completely miscible in liquid state and completely immiscible as solid. So liquid plus solid A, liquid plus solid B, solid A plus solid B, and liquid. So you can see here paste L plus A, paste L plus B, eutectic compositions, solid A plus B, solid curve, liquids, a liquidous curve, eutectic points, eutectic temperatures at which the eutectic points. Now friend, eutectic compositions containing melting, lowest melting temperature over the composition range. Eutectic composition is the composition of two or more compounds that exhibit a melting temperature lower than that of any other mixture of the compound. The primary criteria for eutectic formation is the mutual solubility of the components in liquids or melted phase. Lidocaine and piroxicane, two local anesthetic agents, form a 1:1 mixture having eutectic temperature of 80 degrees Celsius. So friend, phase equilibria is the three component system. In system containing three component but only one phase, F is equal to 3 minus 1 plus 2 is equal to 4. 4 degree of freedom are temperature, pressure and the concentration of two of the three components. Only two concentration terms are required because the sum of these subtracted from the total will give the concentration of the third component, and temperature and pressure are considered to be. So this is the triangular diagrams. You can see increasing B, increasing C, and you can see 100% A, 100% C. So ternary system with one part or partially miscible liquids, water and benzene plus alcohol. Alcohol provides solvations, and this is the binodal curve. So alterations of the binodal curve with change in temperature. You can see ternary system with two pairs of partially miscible liquids. You can see the situations. So ternary system with three pairs of partially miscible liquids. So friends, hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.